So Lydia asked the question, can we explain the difference between kinetic and static friction? And that's a very good question. So we have here an object that is stuck to a surface. Because the object is stuck to the surface and is not moving relative to that surface, then the frictional force that it is experiencing will be a frictional force of just standing there. And the Latin word for standing is stasis. This is static friction. It's standing there. And the interesting thing about static friction is that it is not a fixed or constant force, but it depends upon the other forces that are acting on the object. So if our book here is the example of the static object, right now the value of the static frictional force is 0. How do I know that? Because there are no other forces acting in the horizontal direction, and the sum of forces is self-evidently 0 because my book is accelerating. But if I now push it gently here, I'm now exerting a force of maybe a Newton or 2 with my finger. And the static frictional force is therefore has a value of, let's say, 1 or 2 newtons in this direction. How do I know? Because the sum of the forces must be 0 because the book is self-evidently not moving. So the static frictional force is able to change and increase in value according to the net force, the other forces acting on the book, until it reaches the break-free point, at which point the book begins to move. And you can feel that. You push things before, and you know you can feel that little jolt as it gets into motion. That's your break-free point. Okay? So static friction, and because the static frictional force is able to increase in value, therefore we have Fs is less than or equal to mus times the norm. One important class of static frictional force that operates is when you have a wheel that is rolling. And at first that seems like that's not right, because the wheel is moving. The center of mass of the wheel is moving, and that's exactly correct. But at the point of contact, this point of contact is gripping the road and not slipping on it. Because it is gripping the road, it is stuck to the road as the wheel rolls, right? So a rolling, not slipping wheel without slipping wheel experiences static friction. And that's a little bit counterintuitive because the wheel itself moves, but the point of contact doesn't.
How come wheels are easier to move than blocks?
Great question. Because you don't actually overcome the static frictional force to get the wheel to move. You utilize the static friction force to get the wheel to move. Okay. So the only friction you have is actually at the axle. And if it's well lubricated, it's basically 0. Now, by contrast, if you have an object that's in motion that is sliding past a surface, then that object is going to experience a static frictional force of motion, or kinesis, and therefore you have kinetic friction. And that would include when your car wheels lock up and you start sliding on ice, or whatever, which we don't like to do. One moment, and then we'll do that. Now, Lydia, take all of what we just said here and summarize it in this way. What is kinetic static friction, and what are the equations? Do it without looking up. help her out. She needs to simplify that. When the object is what relative to the surface? Static. Is stuck, stationary to the surface, right? It's stuck to the surface. And then the equation? So it's really an inequality set equation. Joseph,
Can you go on to page 11?
yep. Peter,
Down on my phone.
I was just gonna ask, let's say the mu becomes 0, is the wheel still gonna roll or is it just gonna slide?
that's a great question. If the mu is actually 0, then it's impossible for the wheel to roll.
Well, if it was like rolling before it turns to 0,
Yeah,
well,
it
if
actually
it's
has to
rolling,
continue to grip in order to continue to roll.
so it's gonna stop rolling.
So, for example, if you're driving a car
Right.
and you're driving along pavement and you hit a slip spot, your wheel will not continue to roll, or not continue to roll very much because it can't grip the ice very much. And instead, it will just begin to slide.
It'll still spin.
It might spin freely if it's already in motion, but it won't be doing any gripping. It will be slipping as it goes. Yeah.
Does friction have any effect on bouncing?
On bouncing
Yeah.
or balancing.
Bouncing, like ball bouncing, or
A bouncing ball is going to experience a collision with the floor, and that collision is not totally elastic, as you know from your lab, right? And so the question is, where is the energy lost? And it's mainly due to internal compressions within the ball, not so much a frictional force to the side.
So, like, if you bounce the ball forward, would it use friction to keep going forward, or will friction keep it from going as far forward? You know what I mean? If you bounce
Oh, in
it,
other
will
words, you
friction
bounce it
reduce
forwards,
its
and
speed?
you've got a ball like so, and the question is...
Friction reduces x speed a little bit.
Yeah, actually,
Couldn't it just go the other way?
if this were a frictionless surface, it would just bounce off of that frictionless surface.
But, like, would friction slow down its x speed at all?
Yeah, possibly a little bit. Yeah, possibly a little bit. Hand over here.
Oh yeah. Can tire go fast enough on a script level, I guess, to where it would the friction would be too much and it would flip?
Yes, that happens all the time. If you try to accelerate too fast in your car, what happens?
It flips.
Yeah, it slips. You feel that.
Right.
And so the way to think about that is this: because you have a maximum or a cap on that frictional force, right? And we think F equals ma. If the friction is the one thing supplying acceleration, if your wheel accelerates too quickly, it will exceed that US times an old, and it will be able to slow. Yep.
And how come that happen? Oh, that usually only happens when you're stopped. Why can't you do that once you're ready?
Your acceleration faster.
Oh, I see.
Because it's hard to peel out once you're in UPL.
It's because of the gears, actually. So when you're in fifth gear, it's not possible for you to accelerate your tires fast enough. Only in first gear can you accelerate your tires fast enough to actually peel out. Yes.
My question is, why are we doing this? Out here today, and why are we using report?
Oh, this means you did not watch the video lesson.
I watched that.
Okay.
Watched it. Then I had some
That's your question. Okay, so back to your question of reading. So you feel kind of overwhelmed with the book, and so now what are your questions?
With the reading?
Uh-huh.
Or, like, you mean how to follow it, or about the reading?
Yeah, either way, content or form.
I think this will make me seem very not bright, but
Don't worry about
sometimes
it. We're all friends.
sometimes when I'm following it, I'm going through the examples and say I'll go through it in my head. Okay, they get from this to this. Sometimes they'll skip their entire ways of how they got there, and they'll just put arrow answer, and and it'll have the equation, arrow, answer, and it'll
Yes.
say, this leads here. And it had a huge equation, and it gets down to just 2 letters, and I'll know how did they cancel out, what did they do.
How did they get from here to here? Yes, absolutely. I've had that experience a lot too when I read math. And what I have to do when that happens is I have to actually work the problem, and I get to this point and I say to myself, what would I do in order to solve this equation? And then usually, as I work through and try to solve that equation, I go, oh, that's how we do that. So it's actually the working of it yourself that solves that issue. But you guys all know what he's talking about, right? It seems like magic. Whew. It's not magic, but to find out how it's not magic, you have to drill down into the details. Yeah.
Sometimes like the equations are used and
Yes, I hear that.
yeah, that's definitely different.
And I try to sort of normalize those. There are 2 things that can happen. One thing that can happen is you have same equation, different symbols. And so the way that you'd recognize that that's happening is that you remember we did an equation, but it had slightly different symbols, and so you compare it back and you say, okay, they're just labeling this different, and that's okay. The second thing that the book will sometimes do is that they will use, we might call them minor equations that are not ones that need to be memorized. And I'll give you an example of that. The range equation kind of falls in the category of a minor equation that doesn't need to be memorized.
And the thing that's really confusing with those equations they get is all the subscripts. Like, I don't know, those make me confused too. Like, all the little subscripts that we don't really use. We don't really use those, I feel like, a lot.
Okay. Find a good example of that in your book, and we'll piece that together. So minor equations that don't need memorizing, and here's what I mean. What I try to do with my teaching is I try to teach big ideas that will solve a wide variety of problems, right? So in the forces chapter, what is the big idea?
Of course, it goes in that.
That's it. Newton's second law. And to get there, what's our tool of choice? Free body diagram. That's it. And so from my perspective, if you start with the free body diagram and you apply Newton's laws, then you get there. What they will do is they will actually do that process for certain specialized situations, maybe 2 masses on a pulley or something like that. And once they have gotten those 2 masses on a pulley, they now present an equation that comes out of that process. Something like acceleration equals m2g over m1 plus m2. And you're sitting there looking at that equation and you're thinking to yourself, was I supposed to know that equation? And the answer is no, actually. You don't need to know that equation. You don't need to memorize it. You need to see instead how it came out of the process. So if you work the process, then you get the same equation and you go, oh, okay. We don't have enough brain cells to memorize all of the equations that the book throws at us. And that's a thing that's peculiar to physics. Math textbooks don't do the same thing. But physics textbooks will do that. They'll have a big idea, and they'll apply that big idea to different situations, and they'll come up with different equations. If I were an engineer dealing with masses on pulleys all day, I would probably end up memorizing that equation out of self-defense, right? But if I'm just a physics student, then I'm going to really focus on the big idea. So, how does this answer your question? I think it answers your question this way. First, you ask yourself, is this the same equation as the one we did in class, just with different labels? And if it's not, then ask, how did they get that equation? Work through your process, and you should see it pop out. If that happens, don't worry about memorizing it. And if you're still in doubt, you can ask the next thing. Good. Did you find a good example, Heidi?
Well, like, there's the one with, like, okay, so, it's like f of x, and then, like, I don't know what f of t is, and then there's the x that they throw in there, which, like all those little subscripts, I just don't like all of that at all.
Ah, okay. Right. So first of all, when you're dealing with symbols, you gotta take a look at the diagram they're referring to. So in the diagram, they're referring to three forces, and the way that they do those forces is they throw subscripts on them. And there you go. So FP is like this, is that right?
Yes.
And F,
Why is it P?
good question, hang on a second. And FG is straight down, is that right?
Mhm.
And they've got
Well,
FN,
NG.
oh, they have MG?
Yeah.
And then they have FN straight up? Okay. Yeah, it'll do. Alright.
Yeah, what is that mean?
Yeah, so what is FP? So we go back to the diagram, and in the diagram, what explanation do they give for these forces? What page are you on so everybody can follow you?
86.
86. We're on page 86. Everybody take a look. And they show an X and a Y coordinate here. Okay. All right. So if you go up to the example at the top, the text that comes first we call the stem of the question. And the stem of the question says, suppose a friend asks you to examine the 10-kilogram box, hoping to guess what's inside, and you respond, sure, pull the box over to you. She then pulls the box by the attached cord, as shown. The magnitude of the force exerted by the person is FP equals 40 newtons. Right there, that sentence announces what FP is, the magnitude of the force exerted by the person. And what do you think the P probably stands for? Person, or maybe pull, or maybe both, right? So the FP is that. This is just identifying which force we're talking about. That's it. I myself am not a huge fan of the subscripts. I would love to do this one like this. Normal force up, mg down, and a tension or maybe a pulling force, T, like that. Right? Why do you think they do all the F's? What do you think the F's are there for? Because it's to remind you that there are forces, which remind you in turn that certain things show up on free body diagrams, forces, and nothing else. Initial velocities, whatever, don't show up on free body diagrams. So that's why they do that. But all it is a label. Now let's talk about the X part. This tension, or this FP that we have here, is off at an angle, right? And you remember that what we do with forces that are off at an angle is we resolve them into components. So I would scratch this guy out and replace him with his two components, and his two components are the X component and the Y component, just like that. And as you know, the X component is going to be FP times the cosine of the angle. And the Y component is going to be FP times the sine of the angle. Okay? So the X and the Y are simply giving you direction, X and Y axes. When that happens, if you're looking at some kind of a variable, and all of a sudden you have variable sub X, variable sub Y, variable sub Z, you can be assured that they are just giving you components in particular direction. Does that make sense? Does that help?
Yeah.
Good. Other questions about the reading? Okay, questions about homework problems that you tried to work? Yes, sir.
23.
23. You did that one?
Oh, yeah.
I like 23. 23 is a good problem. Tell us what you did with it.
The reason why I said because I didn't do it yet. So I didn't want to.
Yeah, no, I'm not going to do it for you.
Yeah.
So you got to do it, and then,
I realized that.
yep. Anybody else? The one with the 2 buckets. 25, sure. Tell us what you did with it.
Well, I don't understand how do you do the second part? Because I get the tension on the first one, you just add the 2 bucket weights, right?
Not exactly.
Then
Tell us how you did, what you did with this. So we're looking at number 25 here, and the problem presents 2 buckets like so, and they're asking, what is the tension in each cord? And B, if the buckets are accelerated at 1.6. Yep. Okay, so what did you do? Sum of forces on what?
well, it's not going anywhere. They're just
Okay, you say it, but I look and I see 2 it's on them. Aha! Notice what you did there. You're treating the 2 buckets as a system together. Okay, right? So are you allowed to treat it as a system together? Well, okay, so first of all, there is no cosmic rule. Thou shalt or thou shalt not treat it as a system. But let's ask a different question. What information can you get out of this problem if you treat it as a system? If you treat this as a system together, you're basically replacing your 2 buckets with one big mega bucket. You see what I'm saying? I'm taking this whole set of objects and I'm replacing it with one big object. When I do that, then I still have this cord right here, and I can find the tension in that cord right there, but I lose the information about this cord right here, and I will not be able to find the information about that cord right there. So, we get some trade-offs. It's probably simpler to analyze this, but I don't end up answering every single question. Is that a trade-off that we're willing to make? Yeah, exactly. So I think we're going to have to no longer do them, but instead we're going to have to deal with the buckets as individual objects. Bing, ding, ding! That's what I was trying to get you to say. That's exactly it. Go ahead. Now, it's implied in what you said there is that the first bucket is this one right here, right? So the first thing that has to happen is you're going to need to label those guys 1 and 2. And Heidi, here's where the subscripts are going to come in because we had to label our buckets 1 and 2.
Yeah, those I can understand why you.
Gotcha. All right. Okay, so we take bucket number 1, and now tell me what we got here. Mhm.
But then that's also how do you do it?
Huh?
Well, I guess it now it's just
We're looking at bucket number 1. Don't we have a rope there?
Yeah. And so NG equals 3 or
MG plus.
Right. See, the beauty of the free body diagram is that you don't have to resolve the math questions. All you have to do is say, hey, look, there's a rope. Hey, look, there's a force. But there's one slight thing that's wrong with my free body diagram. The way I've labeled things. What's wrong with the way I've labeled things? I do have to separate the two T's. How am I going to do that? T1 and T2. I cannot assume that these two tensions are going to be equal because they are in different ropes, right? So your free body diagram for this one looks like so. All right, good. What about bucket 2? What does it look like? Good. And MG pulling down. Are the two buckets of the same mass?
Yes.
Are we told that mass? Oh, 3.2 kilograms. That's a lot of bucket. So mg is equal to what value then? Uh-huh. 32 newtons. And mg here is the same. Okay? Excellent. All right, now let's talk part A. Part A wants to know what is the tension in each cord when these buckets are at rest. Uh-huh. And I'm going to just go ahead and call that 32. Which equals 0. Exactly so. All right, good. Keep going. Equals 0. Excellent. Now we look at this. Yeah, that's right. That's exactly right. The algebra pops out immediately. Now we look at this system and we do a quick variable count and an equation count. How many variables do we have? 2. How many equations do we have? 2. We should be good to go. And in fact, we can do this by substitution because I can solve for T2, and what do you get, Lydia? Uh-huh. Uh-huh. Now notice here is a poof moment. Joseph, I think you were asking about this question. My work shows T2 equals 32, and then poof, T1 is equal to 64. So I'm reading that. To follow that, I would say, okay, what do we know? We know T2 is 32, so I would go ahead and do the algebra by plugging in the 32 there and seeing, oh yes, I get 64. So math and physics, sadly, are not spectator sports. Instead, you have to actually get down dirty into the details and follow. Great. All right. Now, what changes in part B? We have an acceleration. So how does that change things? First of all, does it change my free body diagram? Second of all, does it change my equations? Good. So how does my sum of forces on one change here? You say that the left-hand side is going to remain the same, but now the right-hand side looks like what? Mm-hmm. And notice that I'm using the mass of just this bucket because I did the sum of forces on just that bucket. Right? Force sums. And go ahead, keep going. Sum of forces on 2.
The same way.
Uh-huh. And over here, yep, same thing. Yep. This is going to be 5.12 newtons for each. So keep going with that thought.
So,
And then plugging back in here. Is it 69? No, it should be 74.24. Your T2 is bigger, and also it's equal to 5.12 newtons.
yeah, so you add 32 plus the 1, 2,
That to the 37, yeah. Yeah. So you get 74.24 newtons for that guy.
Okay, well, my problem, I didn't know what to do with the, so tension is just
Tension is just a force. Yeah, that's exactly it. And that clears up any mystery that there should be about the test question. About tensions. It's just a force. Good. Other homework questions? Well, this is a delightfully lively discussion. Okay, I'll throw it up. I like 27. Number 27, 2 snowcaps tow a housing unit to a new location in Muerto Base, Antarctica. One of my former students is currently doing the IT for NASA in Antarctica. How cool is that? That's it. You met him, sir. Yeah. Is he handy? Yeah. What's that? Awesome. So let's see here. The sum of the forces exerted is parallel to the line, and FA equals 4,500 newtons. Determine FB and the magnitude of. Okay. They give us a really interesting explanation in this problem. They say the sum of the forces exerted on the unit by the horizontal cables is parallel to the line L. And FA equals 4,500 newtons. Now, question. Some of you are looking at this problem. If you're not looking at this problem, get to where you can see a book so you can look at this problem. I have a question for you. Notice that in the first instance of mentioning FA, they notate it like this, and the F is in bold. You see that? And the second time that they do it, the F is in italics and there is no arrow over it. What is the difference between those two FAs?
One's a vector.
Yeah, that's right. And the other one, scalar, and it gives just its magnitude. Good. Very good. And now what they want us to do is to determine FB and the magnitude of FA plus FB. This is an example of a question that doesn't make sense on first read. And so we figure that there's something about this where we need to have an aha moment. What do you think that we need to do for ourselves in order to generate that aha moment? Okay, we have a picture.
It's asking for the magnitude of FA plus FB.
No, we don't have anything about FA plus FB. That's exactly right.
It's all FA plus
Good. That's a good idea. Maybe we should draw FA plus FB. Here's what I'd like for you to do. I'd like for you to chew on this question for about 3 or 4 minutes. Make as much forward progress as you know how to make. And you had your aha moment. If you've not yet had your aha moment, I should mention that one thing that I do when I'm looking for it is I put in the stuff that I know into the diagram. So I know that this is 45 newtons. Go ahead and mark that fact. And that might give you some inspiration. Catherine, you were inspired. What was your inspiration? I can divide them into X and Y components. Good. How many of you figured out to do that? About half of them. Okay. I want you to be thinking along those lines here, because you know that we're going to be trying to add these, because the problem talks about the sum of FA plus FB, right? And the only way to add them is in components. So something in your brain should fire, I need components. Let me just do that and see where that gets me. Okay. Catherine, when you did components, What did you get for your two components? Ah, interesting you said 40, because the 40-degree angle is this angle right here. And I agree with you. This one should be 4,500 sine 40. And this guy right here should be 4,500 cosine 40. Just like that. What numbers does that turn out to be?
Like 30,447 for the cosine, and then for sine was 2,000.
2892?
Yeah. Well, it's 2893 around.
Close enough. Notice that these two should be close to one another because this is close to a 45-degree angle. And this guy should be less than this one because the 50-degree angle is larger. It's more horizontal than vertical. This was the key insight, dividing it up into components. From here, it's a fairly easy trick to figure out what's going on. Tell me why.
And you can figure out the force of the other one.
Yes, that's right. What do I know about the force of the other one?
That it can be solved with the other numbers.
Yeah, okay, but be specific. Be specific.
Oh my god.
Wait, what did you just?
Okay, so far we've got this guy into components,
Yeah.
and now we figure that we should be able to figure out FB from that information.
Well, because if you, I don't know. I think what I'm gonna say is wrong.
That's okay. You're allowed to say things that are wrong.
Because if you were like add and put them together, I guess. And then some.
Okay, good. So what do we know about when we added them together? We're told something about when we add them together.
Like the total, angle, I guess.
What word in the stem of the question refers to adding? Yeah, that's right. So we're told something about the adding of them together. When we add them together, we're told that sum of forces exerted on you is parallel to line L.
So would it be equal?
It would be equal. In what way? Yes,
Maybe in the x direction.
in the x direction they have to be equal. Because in the x direction, they have to cancel each other out. You see that? So that means I can automatically say this guy is 3447 also. And so this was the second key insight in solving this problem. Don't you hate it when you're going to sneeze and then you don't? Yeah. Okay. How would that help me to find FB though? I'm missing still a y component. What you got?
Well, I did. So now you have r cosine of 60 equals 3447 for FB,
Good.
and then you just solve for r.
I'm just going to write that as FB cosine of 60 equals 3447 because FB times the cosine of 60 gives me the x component, and I know the x component. So I can reverse engineer the magnitude of the whole vector. What did you get for FB?
That is 5,784.
Good. Now before you guys leave here, let's talk about how you would finish this problem. We have found the magnitude of FB. Check. How would we find the magnitude of FA plus FB? What are we missing that we need still? But it's easy to find. Force in the x direction is 0. What about in the y direction?
We need r sine.
Exactly.
Yep. We need this guy still. So we're still not quite done with that. It's just a simple computation, and we can.
Do you want to report the-
Yes, please. I want to make sure that you're doing what you need to be doing. Did you use the simple shortcut?
Well, yeah, but I'm just.
No, because I said
Did that-